It's Friday. What up, everybody? Friday. It's almost the weekend. How is it going? We got a new template here. I'm gonna start that really quick. There we go. We got a new template. I'm finally making upgrades to, or changes. I don't know if they're necessarily upgrades, but making changes uh, to the channel little by little. Working on it little by little. Just trying to make improvements here and there wherever I can. Hi, everybody. Again, I'm Shark Party. If you are new to listening. I am a fourth year graduate student in a kind of degree or program, kind of fusing social psychology and neuroscience, um, with like a strong emphasis on the social psychology part. But we use like neuroscience and neuroscientific methodologies to kind of approach some of our questions in social psychology. So I'm a fourth year graduate student. I'm currently writing up what's called like a dissertation proposal. I'm proposing what I want to run as my dissertation or my final project. And yeah, it's a lot of work. It's very challenging, and I'm just trying to push that along every day as well. So the channel is also being pushed a little by little, but yeah, so it's exciting to be able to unveil new little changes here and there, and I'm always happy to hear any feedback from anybody. I'm gonna take a quick sip before we start getting into the topic of today's statistics. So if you're absolutely new and this is your first time listening to like a Science Friday, so typically on Science Fridays, the topics, this one today I chose myself, statistics, they're typically derived from like, or inspired if you want to call it that, from something I have to attend every Friday as a graduate student. It's called seminar, or like it's like basically a big meeting between a lot of scientists and grad students and well, yeah, faculties, like faculty members and all of them. And basically what we do is we just go attend a meeting and someone gives a talk, a scientist or researcher or an academic from a different university or different institution, and they just share their research, what's kind of currently going on in their world. And it allows us to kind of exchange ideas between labs and things like that to kind of, learn from each other and grow as a science. And I really like the topics that are talked about there, but and one of my issues is that a lot of these topics, a lot of the research that's happening, it's very fascinating, very relevant, very like, to me, it's very important in a lot of senses. But the kind of, I don't want to say detriment, because I don't really see any way around it, but kind of one of the things I feel when I sit in there is like very fortunate to be able to listen to the science like firsthand, just being able to listen in the now. And that it probably won't reach the general public in for years, because it will take some time to verify the theories that they're talking about, to like replicate their studies, publish their studies, get it out into like journals. But they're going to be in scientific journals, so not everyone is really reading scientific journals every day. But get into the general public's hand will take a while, because after publication it might make it to universities. They might start teaching college students, and college students might start talking about it to their friends and stuff like that. I don't know. We don't have to detail the entire process of how this gets to public, but essentially it takes a lot of time. And I'm just kind of sitting here like, what? But it's inspiring to like kind of hear some of this research. So both inspired by that science that's currently happening and Science Friday from National Public Radio, NPR, I thought it'd be kind of cool to talk about the science that's currently going on with anybody that wants to talk about it. So Science Friday was born. Now, what I am not going to be doing is I'm not going to be teaching. So today's talk is statistics, but I'm not teaching statistics. We're just going to chat about it, how it's kind of, I'm just going to give like a general view of what statistics kind of are in terms of science, and then how can it be applied to our daily lives. That's kind of where I want to drive this conversation, is understanding a little bit of statistics can kind of help us digest information when you're given a lot of numbers and things to crunch, like the average salary in this country and things like that. And I will give an example using average salaries in countries to kind of illustrate how a misunderstanding or not understanding statistics can lead you to vastly different perceptions of reality, even though the math might be right behind the statistics. And we'll get into that. So Science Friday, I chose statistics. I'll explain that in a second. But today, or Science Friday, sorry, in general, Yeah, are derived from that. And I want to stress that I'm not going to be teaching the topics, and I'm also not going to be reporting exactly what those scientists are saying, because the last thing I want to do is play a game of telephone, right? We all remember when we were kids, or maybe we still play it till this day, I don't know, of playing a game where someone starts with a secret on one side of the room. There's like, 10 plus people lined up, and you have to whisper a secret across, chain it across, and then the last person to hear the secret like kind of repeats it, and then you see how far off you were from the original secret. And it, like 99% of the time, it is always the case that the message is completely different. And so I don't want to do that. So for Science Fridays, I'm not going to be sitting here just reporting trying to remember everything, taking notes furiously, all their stats and all their figures, only to try to report it 2 to 3 hours later, because my seminars do take place every Friday. That's when I attend the kind of science lectures every single Friday. So it'd be impossible to do that, and I don't want to spread misinformation. That's like the opposite point of my channel here, hopefully. And yeah, so I'm trying to avoid that. So instead, we're just going to use the seminars as like a starting point, or a chatting point, and we can all just talk about it. And if people are interested in like what the researchers were doing, like the topic, like, okay, well, like that sounds like a cool topic, but like I actually do want to find out what the firsthand science is saying. I'm happy to like provide links and stuff. Usually professors have lab websites where they have publications and stuff that you can read. I'm happy to share links and stuff, or just links to general knowledge about the topics, or just chat about it too. I can chat more in depth about it, but yeah, so if anyone at any point, feel free to ask or anything like that too. I do want to make a quick plug for the Discord channel if you are seeking to just kind of have a platform to like just chat about topics that we chat about during live streams, or if you're listening to this on like a recorded version, YouTube or here on Twitch, and you are just curious and want to chat about it on on a forum or something, there is the Discord channel. You can just get an invite by attending any live stream, typing !Discord, or on my Twitch page, or you can go to twitch.tv/sharkpartygg/about. So on my about page, you'll see a little join us, and you can click on that little badge, and that sends you an invite. But you do have to have Discord, of course. And Discord, if you're unfamiliar with that, it's like a chatting platform, kind of like Skype, but a lot of gamers use it. It's just a nice platform, very user-friendly. Cool. So today I wanted to talk about stats because this week so right now I'm TAing for a statistics course, and this week I had to teach my lab section about the t-test, the independent samples t-test. What's up, SPS? Welcome back. I'm here, dog. I'm just playing games with friends, so I'm just passive support, but I'll chime in. Okay, sounds good. We're talking about stats, so if there's any point you want to chime in, you're going to want to chime in during the example. I think people like that the most. But I'm going to first talk a little bit about kind of what statistics are. But so anyways, I was kind of inspired to talk about it and it's fresh in my mind, because I just taught this week's lab section was on the t-test, independent samples t-test, so comparing two different samples to each other and seeing if there's a difference. So I was just teaching it, and it can be rather tough to like really grasp what's going on and what statistics are doing, what they're telling you, and it can be rather tough to interpret statistics just on the first whim, on the first go. And so yeah, I just kind of want to start just chatting about statistics in a very general sense. Again, I'm not going to try to teach. I'm not here to teach anyone. I'm here to talk about things and answer any questions if anyone has questions about like education or anything like that, or the educational process, or if they want to know like experience of a grad student. I'm happy to talk about those things at any time. So yeah, I'm not going to teach stats. So I just want to start I feel like sometimes we kind of misperceive what statistics are, or we might set up this image that it's really hard, or only like really smart people can understand it. And just that misperception of like thinking, okay, you have to have so much knowledge to be able to understand something complicated like stats, that you sometimes just miss it, like completely miss what it's telling you, because it was actually way more simple than you made it out to be. Like you kind of ignore the super simple answer to things. And one kind of example I can give of that is when a lot of, introductory people to stats, that you hear t-test, we're going to perform a t-test. It sounds like there's a lot going on in the background, but in reality, in a very, very general sense, in reality, all we're really doing is just doing a subtraction problem and trying to divide out the error. That's kind of what the t-test formula is where you're subtracting a mean from another mean, and you're dividing out some sort of variance or standard deviation. So in other words, kind of like error, and you're just seeing if it equals 0 or not. right? In a subtraction problem, excuse me, something that caught my throat. I'm going to drink water really fast. Okay, so in a subtraction problem, so in math, to compare two numbers, right, I like to always start off with students to try to get them to think in different ways of statistics instead of just approaching it really like negatively, like, oh, it's going to be so hard and I'm not really good at math, or I'm not really good at understanding like these complicated things. Some people just have a lot of self-doubt. Other people don't, and they're good to go and they understand these things very straightforward. But if you're just one of those people that self-doubts a lot, sometimes that is the case. Our massive misconception or misperception can make a barrier to an otherwise more easy topic. So I like to kind of start people by thinking about statistics in a very general sense, about like just asking them like, okay, in math, how do you compare two numbers? Like, forget about the greater than, equal, or greater than and less than signs, but like using a mathematical equation or function, how do you compare two numbers? How do you know if, and when I say compare, it's how do you know if two numbers are equal? Right? So the way to do that is subtract them. And we're like really, I think it's like we're really used to subtraction from like elementary school. We don't really think of it in other terms. We just think of it as you're just taking a value away from another value and that's it. But in reality, think about it. So what happens if I have 5 apples and I have a basket over here that I haven't counted at all? I haven't counted this basket, but I just subtract them and I get nothing out. Then I know what was in that basket. It was 5 apples. And that's how I know I'm kind of comparing how many apples are in each basket. Well, if I subtract them from each other and I get a 0 result, they were the same. If I get any other result, then one value was different. And going back to math instead of apples, because it wouldn't make sense to get into negative apples, if we were comparing, and I'm going to make a very basic example, if we were comparing 4 to 5, right, and you had 4 as your first number, you go 4 minus 5 equals -1. That -1 indicates that that first value is less than that second value, right? That's kind of the logic here. And when you start to kind of conceptualize your subtraction problem, I was like, oh, wow, that is kind of like a comparison problem. I just see people understand t-tests, f-tests, and z-tests and other statistics because the formula is a subtraction problem over, the numerator of a division problem, right? If you're unfamiliar with this terminology of math, a numerator is kind of the value. If you have a fraction, right? The value on top is your numerator, and you have your bar, and then the value on the bottom is your denominator, what you're dividing by. Okay? So on the top, for a lot of your statistics formulas that you'll see in at least in the science, and when I'm talking statistics in the way I understand them, the way I'm describing them now, I do want to make a note that it's in psychology and like in social psychology and applied sciences like that. So I'm not speaking on behalf of all the sciences. I'm speaking on behalf of like kind of my experience with it and students. But a lot of this math and a lot of logic applies to other field statistics and just math in general. So that whole comparison thing, that's just another way of reframing a subtraction problem. It's still a subtraction problem. I didn't change it at all. It's still a subtraction problem, right? And just if you use algebra for that subtraction problem that I set up, the 4 minus 5, right? Or yeah, I guess let's go back to the if I wanted to compare 5 to 5 with a subtraction problem, I would know they're equal because 5 minus 5 equals 0. The other way to algebraically manipulate this formula to prove it is add a 5, right? 5 minus 5, you can add 5 to one side, but put it on the other side, and your formula now becomes 5 equals 5. Right? If you do that for 4 minus 5, then your formula becomes 4 equals 5, which makes no sense. You broke it. So that means they are not equal. So you'd have to put 4 does not equal 5. Does that make, I don't know. I said, does that make sense? I feel like I'm back in my TA thing. Hey, what's up, Geeky? Welcome. I'm just chatting a little bit about statistics. I just taught my lab section this week on statistics, and I think it's a kind of an important topic to sometimes just rehearse. And I'm going to give an example of real world statistics of how we can use them, or at least use our knowledge of them to like correct our information or to make sure the information we're getting is more accurate. But first, I'm kind of going over what statistics kind of are in my field. And I was just mentioning, so like in math, what do you do to compare two values? You subtract them, right? If you subtract them from each other and you get a 0 value, they're the same value. If you don't, if you get any other value, then they're not the same value. So I was just mentioning how a lot of our stats formulas in statistics, are essentially just a subtraction problem. You're comparing two means, right? You have a group and you want to compare it to another group, because in our science, what we do is we measure a lot of people and human behaviors. So you have how people do X versus how people do Y or whatever. Those values can be whatever you want them to do, but you typically subtract two values and you're dividing by some level of error or variance or standard deviation. So, so anyway, so that comment's funny. Got mad badges. Anyway, so statistics in a sense, so just going back to what I was saying, in a general sense, statistics really is allowing us to compare mathematically two different things. And it allows us to say, okay, there is a difference, but do I care about that difference? So that's where we can say in statistics, is it significantly different? And this is where it can also become kind of tough for students to grasp this concept of when we start to say the word significant, because they're still stuck in English. And this is why it's kind of tough to sometimes for the general public, especially those who've never taken a stats course. It's not a bad thing that you haven't. It's totally fine. But this is kind of one of the issues when the news, for example, the media presents some sort of statistics and you're not trained in statistics, or you don't really understand the language of statistics. So you'll make your own inferences, you'll make your own conclusions, but they might be wildly wrong. And then you go tell your friends, or you go post to Facebook, and then other people might like your thing, and you're wildly all off all of a sudden. So just understanding a little bit of logic of the statistics and a little bit, I just think can help a lot of us in our general lives, which again, going back to the point of today's topic, that's kind of the point. So statistics, in our science, at least in psychology, and trying to understand human behavior and human cognition, things like that, is essentially allowing us to compare two different groups. And again, when I say when we divide by error, usually in our stats problem, that just means we don't live in a perfect world, right? There's going to be individual differences between everyone that we're measuring. We're going to get 200 people to take the same test. What's the probability that 200 people do exactly the same way on a test as 100 questions? It's incredibly low. So there's no way that I could just have a simple subtraction problem to compare my two groups, because there is such thing as error. So what statistics allow us to do is kind of more fine-tune our... Oh, dang, Kiki, thank you. Thanks for the sub. Again, I never expect them, but I always appreciate it. Again, I'm always happy that you're here. Good to see you here, and yeah, I really appreciate it. I like the boop. Anyway, sorry. I got thrown off. It's just the boop got me. And also, anyone listening at any point, if I go too fast, I'm happy to slow down or repeat something. If my music isn't glitching. Yeah, let's pause the music for a second. Let's let that catch up. I feel like I'm lagging. Oh, another hydrate. Okay. All right. Oh no, now I lost my spot with statistics. Okay, yeah. So what statistics allow us to do basically is, yeah, we're trying to control for as much error present in the data. And again, when I say error, error can also come in the form, in our scientific experiments, they can also come in the form of our own human errors, right? We as scientists, the people doing the experiment, we can commit errors, and then just doing the math, we can commit mechanical errors. So there's a lot of error that can be present, and we try our best to control for that error, minimize that error, but nonetheless, there's going to be error. So statistics will then let us know, okay, yes, there's a difference, but do we care about that difference, right? We all accept that there's always going to be a difference between large groups of individuals. There's going to be individual differences. But if the difference between group A and group B is 0.00001 of whatever value you're measuring, do you really care about it, right? In some instances, a small value can indicate a huge change, right? If I say the difference between person A and person B is 1 meter, one sounds kind of small, but 1 meter is huge in terms of heights, right? Because we tend to vary within inches of each other, centimeters of each other. But 1 meter, that's like 3 feet. That's like 36 inches. It's approximately that. I'm not sure. That's a lot in terms of height. So it's relative again. So statistics, so just looking at differences just with your eye is kind of tough to tell whether you have an effect or whether you have something or not, whether you have a difference. How do statistics come into play in medicine? So in medicine, basically, like if you take a psychopharmacological approach, basically, let's just say I'm trying to develop a drug, and I think this drug is going to improve your focus. So let's just kind of take the ADD literature if you want. I think that compared to a placebo, that this, well, I have to have a placebo, right? I have to compare it to something. Otherwise, you can't really, statistics is kind of, you can apply statistics when you're not comparing. But when you want to specifically say or set up kind of like a causal relationship between variables, you're going to need to do a manipulation, and that is going to need to compare to something, compared to something that didn't get your manipulation. So my manipulation in a medical sense could be the drug I'm going to use, and I'm going to try to apply it in a test-taking environment. So if I take group A, they're going to get, the drug, and group B gets a placebo. I have them take a test. I get the averages of their test scores. I, calculate variance, standard deviation, all of that. I compare those, the mean scores of my two groups, group A that took the drug and group B that took the placebo, right? And if their two means give me a 0 value, it means there's no difference. There's no effect of the drug, because the people that took placebo did equally as well, or equally as bad, however you want to interpret that mean. But if there's a difference, then statistics can already tell us that. Is there a difference? And then the difference, let's just say, was 1 point on this test. We don't really know what type of test it is, so it doesn't really, just being 1 point different in mean doesn't really tell you if you should care or not. Like, is that significant enough for us to care? So the statistics, such as like a p-value, if you did a t test, for example, the p-value would tell you, yeah, the difference matters enough that it's like there is an effective drug. And then you can do another statistic called like a Cohen's d. It measures effect size. It can tell you how big the effect size was. Okay, so how much did this drug improve, or you could, maybe it decreased scores. How much did it improve or decrease test scores? And that's kind of like what your Cohen's d or your effect size will tell you. And you're going to have to use different effect size type formulas depending on the situation. I'm just trying to keep this kind of at a general thing. I'm not trying to give like a stats lecture. I'm happy to like talk about them in this way, but yeah, that's kind of the way it can play in medicine. If you're looking at the effects of drugs, you're basically going to be comparing to placebos a lot. In terms of surgeries, I'm not sure. I'm not a medical student, so I'm sure there's like a lot of more procedures in there. But I mean, the stats, if you want to apply certain inferential statistics, so there is a difference, and I might tap into this. There is a difference in types of stats that sometimes you read about online. Yeah, no problem. My pleasure. Any other questions, I'm happy to address or to chat about. That's what I'm here for. So there are two different types of statistics. A lot of the times what we are more used to hearing, or we usually get reported to us, are called descriptive statistics. And people can run wild with descriptive statistics when we shouldn't, because that's what like people like to set up causal relationships, or like to set up a lot of conclusions based on descriptive statistics without knowing that they're descriptive statistics. And I'll tell you, I'll define the difference in just a second. For the second group of statistics called inferential statistics, and that's what I was just talking about right now. When I was comparing two groups in medicine to see who got the better score, right? That was because I used a manipulation myself. I implemented a drug myself, and I want to see, does it have an effect? I have to compare it to another group. That's an inferential statistics, because I'm trying to set up a relationship between drug and test performance, and I want to be able to demonstrate to the public, or to whoever I want to sell my drug to, I want to demonstrate, yes, it has an effect, it works. And so that's why I'm setting up a causal relationship. Taking this drug increases or decreases. We don't know the outcome. I didn't give one. But let's just say it increased it. Taking this drug does increase test performance. Here are all my statistics. And here's my p-value that tells me I care about the difference. Now, the way I wanted to end today's Science Friday, or talk about it more near the end, is how it can go wrong. How you can use all the right math, present it in a different form to other people, and blatantly lie to them, but never have cheated your stats. It's just a misconception of the statistics. But going back to descriptive statistics versus inferential. So I was mentioning that we're all kind of used to, we all get fed a lot on our social medias and news without really knowing that this is what they're called. We get fed a lot of descriptive statistics. And descriptive statistics are things like averages, the mean, the median, the mode, the range, right? What do those things give us in terms of statistics, right? The mean, the mode, the median, the mode, the range, and there's one, oh man, I can't even remember. Median, mode, mean, range. There we go. Okay, sorry. What do those tell us? They're basically trying to describe your data to you in like a summarized format. So if I was trying to say, let's take the medicine example again. If I was trying to say, does my drug, let's just call it, let's call it, I don't know. What do you, I don't know. What's a label that we can all remember for this drug? That way I can keep referring to it. We'll call it focal X. All right. So let's just, going back to that example to describe what descriptive statistics might be. If I had 1,000 people take focal X to see if it improves test scores, and then I want to tell people, hey, what's the average? And people ask me, okay, how does your drug do? Am I going to sit there and report each individual number that each individual person took, 1,000 test scores? Be like, look, this person got a 90, this person got a 90, this person got an 82, this person got a 73. No, you're not going to do that. You're going to give them a mean. You probably will give them a range, because what you're doing is you're describing your data. So that's what descriptive statistics are. So when you're maybe sitting there on your couch and you're listening to the news and they say, oh, the average crime rate of X place or Y place is this, you're being fed a descriptive statistic. You're not being fed something that's causal, but people sometimes will set up causal relationships. They'll start to draw inferences from the descriptors, right? They can start to think, oh man, living that place must cause crime, right? Just like if I say, in the summer, we see the average sales of ice cream go up. You go, wow, summer causes ice cream sales. Well, no, kind of, right? Indirectly. I guess the best example. I guess that was a horrible example. Let me give the best example is in the summer, murder rates go up, but so do ice cream sales. So murder causes the increased sales of ice cream? No, they're just correlated. It just so happens that heat, increases aggression and blah, 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 and heat also increases our desires for something cold, so we go get ice cream. But that's a correlation nonetheless. So going back, that was a kind of a messy example, so sorry. But going back to what I was trying to say is sometimes you're fed descriptives, and sometimes we might try to make causal relationships or try to infer something when we didn't get any inferential statistics. So as opposed to descriptive statistics, inferential statistics is what we've been kind of talking about, comparing things, seeing if you care, seeing if there's an effect, and setting up relationships, causal relationships. And when I say causal relationships, I mean cause and effect. So you do something on purpose and it produces an effect that you predicted that was going to happen. So not by accident. Because if it happens by accident, then it's just random, and your stats, you either misinterpret your stats if they said you were onto something, but it's always random, or you didn't do your stats. You're just kind of living your life randomly. So that's kind of the difference between descriptives and inferentials, and we're very used to the descriptives one. Whew, okay, I'm gonna give it like just a minute, just to see if anyone wants to chime in with anything before I move into a real-world example of how statistics can be like misused to promote misperceptions, if you will. That's a great question. So and I'm really happy to answer it. So I'm happy you're asking it. This is I always encourage anyone listening to ask any question. Doesn't matter if it's on the topic or not. That's what I'm here for. So how do I know what major I should choose after high school? That's a really tough question. I'll give you from my own background. So basically, when I was in high school, I thought I wanted to be I thought I wanted to be a geologist. I thought I wanted to be I was really liking astrophysics, and I also felt like going into engineering would be cool too. But when I went to college, I got really interested in medicine, and so my whole college career I was pre-med, and I'm not in medicine anymore. So answering that question, I can't give you a really clear and cut dry answer like this is the right answer because it all depends on a lot of things. But what I can tell you is it's good to test the waters in a lot of different areas. It's not bad to test at things, and to fail at things is not a bad sign, right? So basically, college, if you will, for me was kind of that experience to test the waters. Like I worked in a hospital, I volunteered with a psychiatrist, I worked in a lab as a research assistant for social psychology research, and all those experiences they were all super valuable. They got me to get my kind of toes wet in those areas and kind of feel out what I liked best or what I kind of was more passionate about and things like that. It didn't come until like way later in my life that I found what I really wanted to do with life, but you know, it's kind of tough. So what I can say though is, what do you want to do? What interests you? What fascinates you? What kind of like lights kind of like a fire? Like what topics you're like, man, I'm just really curious about this, and it can be about anything. You don't have to like think like I have to be in a very traditional science. Like I have to be a person that's interested in space because it's, you know, like everyone's interested in space. No, like what do you like doing? What are you interested in learning like more about? What do you like improving on? So sometimes answering those questions like, okay, like when I was in high school as well, my final semester of high school, I took a psych course, and when they were describing experiments, and just how they had the ability to predict behaviors and get it right to like beyond chance. I was just like, dude, this fascinates me. Like the brain just at that moment fascinated me. I'm like, I need to find out more about the brain. Like this is such a cool organ. Like I really want to learn more about it because I'd taken bio courses. And I was like, yeah, the body's really cool. I'm also just a naturally curious person. I just like learning in general. But like I just hadn't found anything that was really lighting my fire. I just kind of like, yeah, I like geology. I like engineering. I liked a lot of things. So I was like, I don't know what's right for me. But that psych course kind of made me the most curious. And so when I went to college, I was intending to be a psychiatrist because the other thing that I kind of wanted to do with my life, or what I kind of feel kind of fills me with more like joy, if you will, is helping others. I just like it, and I'm motivated to do it. It motivates me to do things too. And so you can call that a selfish thing, but it helps others. So I see it as like positive egotism, right? So what I kind of thought of when I was graduating high school is like, I want to study the brain and I want to help people. Psychiatry. And that's kind of what they do. They understand the brain and they help people. However, as I started progressing in college, I ended up in grad school because as I started progressing in college, I started really loving the scientific method and wanting to really apply it in a lot of social psychological settings. So medicine wasn't necessarily the right path for me. But and I've talked about them previous streams if you ever want to just listen to those. But I'm also always happy to talk about, you know, my whole path up to grad school. But yeah, there isn't to kind of recap it. There isn't like a right answer. It's just more so like who you are. Yeah, I don't know if that makes sense. And it's totally fine to go into college and still not know your major. I don't know where you're from or anything like that, but where I went to college, there is the ability to go in undeclared and just take courses that you think sound cool. Like, oh, I kind of think chemistry might be cool. I think physics might be cool. Or you could be like, I think languages might be cool. Maybe I'll take, you know, like a history of a language, or maybe you're into history. You'll take some history courses, find out you love it, and then you start majoring in it, right? You don't have to have the right answer immediately in high school. It's a long and growing process. And if you're in high school now, you're still going to grow. You're still going to, you know, you're still forming. Your brain is still being shaped. It's still being formed. You're still what's it called? Kind of developing over time. Yeah, no problem. My pleasure. But you're still developing over time. So just remember when you're trying to make decisions and you're thinking these need to be lifelong decisions, also start to account for future you. Like, oh, like what if my tastes change? What if I start to like this? What if I start to like that? It's hard to account for those changes, of course, because you don't know the future and who you are going to be in the future. But just remember that, like, I'm just trying to say this as a means to try to remove stress if you're feeling it. Like, I need to have everything figured out now. I'm going to tell you right now, like, I don't know a single person, my professor, my advisor, my boss, I don't know a single person I've worked with that looks like they have things figured out. I've never known a person to say, I had it figured out in high school. Because we all go maturing, we all go learning, we all go growing, we all fail at things, try again, succeed then, and then love it. Or sometimes we fail and shy away from it. Life can take you down many, many roads. I don't want to get all philosophical, but I just want to say that to anyone listening and thinking they need to have it figured out right now, regardless if you're in grad school even, or older than me even. I don't think that's the case. I think it's like we all have to just try our best and try to just keep pushing every day. So if you're feeling like that, a lot of us feel that way. If you don't feel that way, that's awesome. Congrats. Teach us a thing or two. Anyway, I'm going to go to statistics now. So I do have I'm going to test something out for the first time this time. I'm going to use this over here to paint some distributions to be able to understand when we're given on the news averages. To be able to understand kind of how you can cheat it without cheating the math, I'm going to have to depict it a little bit. So let me see. I'm going to quickly see if this is working. So if I draw a line, I am horrible at drawing, holy cow. Okay, let's see. This is cool though, I like this. So I can draw a line here. This is going to be our x-axis, right? We can put our y here if we want it. Okay. So if anyone's super unfamiliar with graphs, I'm gonna label it as best as I can. But so again, this is x if you're very unfamiliar with graphs, and this is our y. Okay. Let me see. It's not okay. Cool. I hope it's visible to everyone. I hope it's not just on my end that I can make sure it is visible. So there we go. So we got the graph, and what we're gonna do is plot frequency of a salary. So we're gonna okay, let me backtrack. Let's set up the story first. So you're sitting on your couch and you hear the news, and they're reporting the news of country. Let's call it. Let's see. Let me write it down. I'm gonna label the graph here, so that way we can always have it up there. I don't know. Anyone from the chat want to just make up a name for a country? What should we call it? What should we call our country in this made-up story? Any name. I'll wait like 30 seconds to a minute. See if we can get chat to interact with the statistics. You don't have to though. Okay, I'm gonna start thinking of one. But if you're listening now and you have a funny name for a country, let me know. You know, I'm looking for a fake name, by the way. I'm not looking for a real country. I'm looking for a fake name. I want this to be a complete fake story, just so we can illustrate a simple point, but simple yet effective point. Huh, let's call it, oh, you know what? I know what I'm going to call it. Okay, it's going to be called, oh no, that'll be confusing. I was going to call it Fish Fiesta, kind of like Shark Party, but not Fish Fiesta, or what about? We'll call it Jamboree. Oh, wow, I misspelled that. Jamboree is the name of this fake country, okay? So I'll put in quotation marks that way. If anyone like barely joins in, be like, there's a country named Jamboree? We'll call it Country Jamboree. So in this fake country, you're a citizen of this fake country. You're a Jamboree. Jamboree? You're a Jamboree, right? And you're sitting on your couch watching your Jamboree TV. And you're watching the Jamboree news, Jamboree at 5. Sorry, it's just it's a cool name actually. And you're watching Jamboree at 5, and the news anchor starts to report some statistics like, oh, tonight on Jamboree at 5, we're gonna review kind of like national salaries, just to conceptualize how we're doing as a country. I guess I don't know what they would actually say, but they're just gonna go over kind of salaries in the country. Right? And when I was talking about descriptive statistics, I was mentioning those statistics just give us a snapshot of your data. They don't infer much because they're not inferential statistics, but they just give you a snapshot of the data. So when you're sitting on your couch, do you think they're going to give you the solid numbers of each person in their salary? Like each person's salary of each Jamboree salary? No way. They're not going to do that. They're going to give you a snapshot of the data. So they're going to give you probably like means, medians, modes, You know, mode, if you're really unfamiliar with those terms, mode is the most frequent number found or most frequent value in your data set. That's the mode, so the highest frequency. The median is the most central number, and the mean is also called the average. And if you are really unfamiliar with that or how you find it, the average is you take all your values, add them all up, and then divide by the number of values you have. So if I had 10 people take a test, I would take all their scores, add them up, I get a big value, and I divide it by 10, and that's my average. So they're probably going to give you, oh, and range, sorry. Range is just kind of listing what's your most minimum value possible, or minimum value given, not possible, minimum value given by your sample or data, and what's the maximum. So range is literally a range of two, it'll tell you two values. So if 10 people took a test and the worst score was, let's say, a 6, and the best score, let's say, was a 9.8, then it would be, the range would be 9.8 or 2 to 9.8. Or 4, whatever, or 6, whatever I said was the minimum, 6 to 9.8. So even though 0 is a possibility, what the range is telling me is no one got a 0. Everyone at least got 6 points, but no one got 100%. That's what the range is also saying. Okay, so in our fake country, Jamboree, you're sitting there on your Jamboree couch watching the Jamboree Knows at 5. And they're going to tell you a little bit about salaries in the country. And they're going to present graphs because they look nice. And, you know, it makes it look like they know what they're talking about. I'm gonna grab my brush. Okay, let's see, I got my brush. Cool. So they might show a normal distribution. So when we say normal distribution, we mean, and you might have heard this term before. Oh, shoot. You might have heard this term before, bell curve, because it forms kind of what looks like a bell. And a normal distribution is basically, the way it's kind of defined, if you will, is it's a very symmetrical curve. If I were to split it down the middle, it would fold and it would be like completely symmetrical. And what it really is telling us is that the mode, right, the most frequent score, the median, the most middle score, and the mean, the average, are all here in the middle. Like they're all the same value in a perfectly normal distribution. Right here. So if this was test scores, if I had a test, right, we could say here's 100 on my test, and this is a 0. Oops. Here's a 50. So 50% on the test. If I had a perfectly normal distribution, my most frequent score would be 50, the median would be 50, and the mean would be 50. So I'll put mode. And this isn't a normal distribution. Median. Mode, median, mean. And my range would be 0 to 100. But that's in the perfect world. And, you know, in a perfect world, we rarely get such beautiful normal distributions, such beautiful bell curves. We don't really get it like that. So what you can do to try to, or sorry, I just got like a little bit distracted. Sorry, so anyways, so here, yeah, in a perfect world, we won't have a normal distribution typically, unless you set up like a rigged test or something to produce it, then you rigged it. But basically, this is a snapshot you might see in Country Jamboree of salaries as well. You might say, oh, like 100 stands for $100K a year. Right, and Y, what does Y stand for here? So if X is salary, right, if X is salary per year, oh shoot, you can't see it over there. Let me put that over here. If X, in this example, is salary, and salary is money per year, right, so that's a measurement right there. Okay. If that's X, what's my Y? Y is frequency. Is like, how often does this happen in your population? So in a perfectly normal distribution, 50K would be the average salary, the median salary, and the mode salary. So most people are making 50K. Very few people make 100K, and very few people make 100K. So these tails, so in distributions, this constitutes what's called a tail. So you might hear these terms if you ever take a stats course. You're gonna hear these terms. This is kind of the tail area, and this is called the body, right? Okay. So now that we hopefully we're a little bit more comfortable with a distribution, let's go back to the news. Let's understand how the news might present data in a more real world, right? This isn't a perfect world if we had a perfect distribution, or a normal distribution. Okay, let me see if I can just rewind all of it back, or if it's going to stop at some point. Rewind. While I rewind, if anyone has any questions or wants something re-explained, oh, that's where it's going to stop? Shoot, okay, I think I can just erase it then. Yeah, while I'm fixing this, if anyone has comments, and let me hydrate as well. Yes, thank you. My mouth was actually getting dry, so good call. Where's my eraser? How do I increase my eraser size? Let's see. No, don't tell me it's gonna... What? Oh, no, here. Duh. That's it? Okay, you know what? Then we are just gonna clear this. The cut and paste, the cut way. I'm not gonna use an eraser. I'm gonna have to redraw the x-axis. Okay. That's way too high. I need more room, just in case. Okay, so we have an empty plot again. So let's just say that they're going to plot the distribution of salaries in country Jamboree. And it looks like this. Oh, that's horrible. So again, X. Oh no, that's too bright. Let's do it green. X is salary or money per year. Let me see if the shark doesn't get in the way. Okay, and Y is frequency. And when I draw 1 over S, that's kind of like the formula for frequency, like hertz, I guess. But I'm not really talking about hertz, I guess. I guess I'll just write it. This is gonna be hard. I have to write it sideways. I'm gonna write in caps because that's what it's gonna be easier for me to do sideways. Frequency. Period. Okay. Okay. So again, y-axis frequency, x-axis salary in the year, or not in the year, in Jamboree, in 1 year, in one given year, any given year, whatever year you want it to be. So this is what they show, and they can say, and the news anchor can say, okay, they report. I'm gonna put it over here, the story. Story. Oh, I'll put it in. Can I get a different color? Put it in orange. So the story, news story. Jamboree is doing awesome. We are super rich. Just look at our average. Look at our average salary for Jamboree. Okay, so that's our story. Now, what's wrong with that story? There's a lot wrong with it. So that's the news story. It's like, whoa, our salaries, because the average, let's just say the average is reported. I'm not going to draw all the values here for salaries because they're like, it could be from, you know, if we take the US dollar as an example, it could be from like 20,000 to a billion, right? Because we have billionaires in the U.S. There's such thing as billionaires, and there's such thing as people that don't even that make way less than that, right? So the range of salaries for certain countries is immensely big. So let's just say Jamboree is one of those countries. Countries Jamboree, and they report an average salary. Okay, average salary. So they're going to show, look, this is the, and we did the math, and they do the math correctly, right? They go, oh, our average salary is about 500K a year. Like, dang, I want to live in that country. Right? But you get a hold of this distribution. Or maybe they do present it, but you understand distributions, or you understand statistics a little bit, and you understand. And I'm going over this graph to kind of give my message of like why it's important to kind of, if you are sitting a stats course and you're like, I'm never gonna use this in my life ever. You're going to encounter numbers at some point, and at some point it's probably going to be averages, and just understanding what these numbers tell us, because averages, again, can be a descriptive statistic, so it is statistics. Just understanding those, you won't fall for traps like I'm about to present. So here's the trap. Whoa, that's doing great. But what you can be very unaware. So how is this possible? Where's the trap here? Well, the trap is that because of how the math works out regarding average, again, is you take all your values in your data set. So here we're going to take everyone's salary in the country Jamboree. We're going to take all of their salaries, put them together, and divide by the number of people that inhabit country Jamboree, and I'm going to get the average salary. But the big issue there is that the mean is what we can say it's sensitive to like large numbers. So let's just say in country Jamboree you had a person, let's just call it they're the owner of Pamazon, and they are ridiculously rich. They're going to pull the salary. So let's just say your average citizen, or not average, let's just say most citizens, a lot of citizens make like 10 Jamboree dollars a year, but someone makes 10 billion. You're going to add 10, 10, 10, 10, and then one number that only constitutes one of your data points, but one number is huge, immensely huge. It's going to grab that mean and push it all the way up, and that's going to give this really distorted vision of the country Jamboree. So when I say that again, we can say, let me grab a good color here, and we're going to use this. So on this distribution, the mean, remember on my normal distribution, right? Let me just draw it down here really fast. On a normal distribution, we had, let me draw in a different color. I'm going to draw it in green. No, I already used green. Let's do purple. So in a normal distribution, right, we have a bell curve, perfect bell curve, and we said, and we learned that mean, median, and mode, all are here, okay? But we have a skewed distribution. This is called a skewed distribution, what we have here. And if you really want to nerd out about it, it's a positive skew distribution, and you can always tell which skew your distribution is going and which direction, just based on the tail, which way it points. Does it point to positive values or negative values? So a negative distribution will look like this, right? With my tail pointing to the negative side. So anyway, so in a normal distribution, our mean, median, and mode, mean. Okay, I'm going to type it because it'll be faster. Like here. In a normal distribution, mean equals mode equals median. But in a skewed distribution, that's not the case. That's not true. Our mean, again, we have billionaires up here. Over here, we got where's my text? Billionaires. And over here, you don't. Like below this, like this line over here, it just starts being in the thousands. All these salaries are just in the thousands. They're not even in the millions. And this is billionaires, so it's immensely big. So then what that does is it grabs our mean and it just pulls it over towards the tail. So our mean might be way over here. That might be exaggerated, but like the mean in a normal distribution gets pulled, right? If it was supposed to be here, it gets pulled down this way. Our median is not sensitive to large values. It's just the most central value. And the mode is the most frequent. So where's the peak of your curve? It's like right here. So right there is the mode. So let's just say this salary here is 50K. But the average salary being reported is 500K. But the mode, the most frequent that's happening in your population is 50K. The median, let's just say it's 60K. Like it's slightly more, it might be more to the right because there's just more data points to the right. So you might be over here actually in median. So let's just say this is 75K. Again, because billion is so vastly much bigger than the rest, most of our distribution, most of our data is falling in the Ks, not in the millions or even billions. But the mean is way over here. So mean is way over here. We got the median here, and we got the mode over here. So what would have been more honest of the news station, instead of trying to make Country Jamboree look amazing for anybody that's not from there, you know, they're reporting $500,000 a year. The average here, the average salary is 500K. But that's not an accurate representation of reality, right? Very few people actually break that. And that's because the mean is being pulled by the massive salaries that the very few are pulling in. So what would have been a little bit more honest is maybe present the median or the mode. Be like the most frequent salary? Oh, the mode, 50K. Oh, the most middle salary, the middle most salary, 75K. And you're like, oh, okay, that you get a kind of a better image. If you get all three of these put together, you get a better image of what's really going on. Right? If I'm only given mode, I can't tell that there are billionaires there. You just know what the most frequent is. And if you're given range, then you do know that there are billionaires there. So this is what I'm trying to say. This is kind of my driving home point here, is that understanding just even your descriptive statistics, what they can and cannot tell you, and I've kind of gone into that, can be important into understanding our world and the way it's presented to us. That's all. That's kind of my message. Now, if anyone has chats, comments, questions, I'm going to chill here, and we can chat about it. And if anyone's wondering, like, how is this Science Friday? Like, we have to use statistics in science to test a lot of our effects or like our theories and things like that. And if you came in very late, I already kind of discussed that process of doing that. But I'm happy to always reach out if anyone has questions. Whew. How's everyone's Friday going? I hope it's going great. Oh, I really do like talking about statistics. It's fun. So that is all I kind of had to talk about. I mean, I'm always happy to talk more in depth, but it does start to get more lecture-y, and I'm trying to keep this at a very like more fun level. That's what I'm trying to do. I know sometimes I get jargony, and I'm trying to keep it away from jargon as much as possible. But yeah, if anyone wants to take it, you know, more or deeper, if anyone wants to take it deeper, talk about inferential statistics like a t-test or things like that, I'm happy to. But this is all I really had planned because, again, I'm not trying to turn this into a lecture. Cool, in that case, I'm going to start wrapping up, so that way this video isn't like really long for YouTube, because again, all my Taco Tuesdays and Science Fridays they go to my YouTube channel just so they can be accessed whenever, because they do end up getting deleted from Twitch. So they're only on Twitch for like 2 weeks or something like that. I don't remember. But yeah, all of the Science Fridays and Taco Tuesdays do go to YouTube for the most part. And they're just going to reside there for anyone to, if they wanted to watch them. But yeah, I'm going to start to then just wrap up. But again, if anyone wants to chime in, comments, questions, discussions, it doesn't have to be about statistics, about anything. I'm happy to talk about it. But for now, I'm going to just start doing my thank yous. So thanks so much, Kiki. It's awesome to see you back here again. Awesome to have you as always. And again, I really appreciate the support for the channel. Thanks SPS for stopping in again and chatting again. And Kier, I don't know if I'm pronouncing it right. Kier thy red, Kier thy red, Kier thee red, Kier thy red. Thanks for stopping by as well and asking questions. That was awesome. I always have fun talking. And for anyone listening and not chatting, thank you for stopping by and hearing as well. And anyone listening to recorded versions of this, you are champions. Thank you so much, everyone. I hope you have an awesome weekend. I might do gaming streams. I don't know if tonight, maybe. I don't know. But yeah, thank you so much. This was a fun Science Friday. Got to actually draw this time. I think I'm gonna keep this format and use like a whiteboard for other Science Fridays if I need to. This was fun. So yeah, thanks again, everyone, and have a great weekend. Peace.